Alright, this is lecture 9. We're going to take a look at the 555 timer, and remember that it was on our random dice roller that we had, and I told you we'd be getting to that fairly soon, and you know what we use it for. Okay, so we're going to take a look at the 555 timer, and that's the little guy that was on there, the 8-pin timer. We also have one on our breadboard companion. Alright, our power supply that's on there. We use that to change our clock frequency, so we can make it, speed up fast for you guys. That's when you see the LED on there go really fast or really slow. All right, but we want to derive the characteristic equations for charging and discharging of the capacitor. Okay, we're going to talk about period, frequency, and duty cycle. All the same kind of thing that we did from signal analysis in the last lecture. All right, and then we're going to do a couple examples that you guys are going to have to do on your homework assignment as well. So let's dive right into it. So if you remember, I just said it was the little 8-pin guy that's sitting right there, and you can see on the top that it's 555CN. All right, N just has to do with the transistor that's inside. You might see a P or things along those lines. All right, so it's okay. LM. We're going to go through a data sheet that goes through what all the different tagging is on that. Notice the circle on it though. That's your reference point so that you know which way that had to be put in. Remember, if we didn't put the 555 timer in right into our dice calculator, things weren't going to roll right, and we accidentally put ground where power is and that sort of thing. Okay. So, but it's what we use to create time delays or oscillations. Remember, oscillations in signal analysis is a signal that's going up and down. So we had our square waves, or we had our sine waves and things like that. All right, we can control the time delay with a combination of resistors and capacitors. They're called RC circuits. There are RLC circuits, resistor, capacitor, and inductor. We're not going to get into those yet. That's an advanced course that you can take with me. But an RC circuit, all right, it's how we can control oscillation. All right, if you remember when we talked about, just to review, right, resistors, those control current. So the larger the resistor, the less current. The smaller the resistor, the more current. Remember what a capacitor does when we talked about that in components. A capacitor stores charge. All right, it's not a battery. It can store a charge and then dissipate a charge. But we have to be able to, it has a certain amount of time that it takes to charge and discharge. Now, it's not like super long, but I mean, we're talking milliseconds or microseconds, it's not seconds to you and I sort of thing. All right, but they're both controlled. So when we want to control the frequency of the oscillation, we're going to control it with 2 external resistors and 1 capacitor. When I'm saying external, that means they're outside that chip. We're going to go and see what's inside that chip here in a few minutes. Well, we're not going to cut one open, but you're going to physically see, what it looks like on the inside of that chip and what's going to those pins. All right, but we are going to control it with 2 resistors and 1 capacitor. And then we're going to talk about how we use the 555 timer in there. All right, so the capacitor I just reviewed for you, right, stores charge, and then the rate at which it stores and discharges, because every capacitor can store charge and every capacitor can discharge. All right, is based on, there's a rate. Okay, it's called the time constant. We call it tau, but it's just taking the resistor value times the capacitor value. All right, and that's going to give us a tau. And what we're going to learn in the next course, electrical components, is every resistor or every capacitor takes 5 time constants to charge and 5 time constants to discharge. And tau is that time constant. We're not talking 5 seconds to charge and discharge, 5 time constants. And that time constant is specific to the resistor capacitor circuit that you create. All right, but like I said, we're going to get more into that in the advanced circuit, but this is just a brief understanding. We're going to solve a whole bunch of circuits later on involving resistor and capacitor in the next course. All right, but we're going to start understanding the basics of a capacitor charging and discharging. All right, so make sure that you pause and write down these equations because you will need to know them on your tests and quizzes. All right, so what's going to happen is if we look at a capacitor charging cycle, so let's look at this basic circuit right here. We have a 12 volt DC supply on the left hand side. We got a 2 kilo ohm resistor. We have a switch. That switch toggles between A and B. Alright, and B is a 3 kilo ohm resistor. So what's happening right now? The switch is not connected to B. The switch is sending 12 volts to the capacitor. Okay, we're sending 2 volts or 12 volts to the capacitor through the 2 kilo ohm resistor. What are we doing? We're charging the capacitor right now. Okay, the most the capacitor can ever charge up to is 12 volts. In this particular case, it can only charge up to what the supplied voltage is. So this charger, or the charge on this capacitor can only get up to 12 volts because that's the supply source. If we had a 5 volt source on here, it would only get up to 5 volts. So hopefully that makes sense. And we're looking at the charging cycle right here. Alright, so the equation for charging a capacitor, alright, is the V final, that's the final voltage minus the initial voltage, times 1 minus E to the minus T over RC. RC is the tau, the time constant that I talked to you about before, and then plus the initial voltage. So this is the equation for calculating how we charge a capacitor. And this carries through. If you don't remember E, you may not have even learned about it in class, in math class or science class or any of those yet. But E is the base for natural logs. If you ever remember talking about logarithms in one of your math classes, you may or may not have gotten there yet, or even in science class, okay? If we have a log and you see the button on your calculator that says log, log has a base of 10, and then there's a button on your calculator that has ln. Okay, that stands for natural log or log natural, all right, however you want to say it. It has a base of E, all right. Logs are going to be tied to log scales, kind of just another way that we solve exponential functions, essentially, or we solve when we have an exponent that has a variable. You're going to hit natural logs and things like that. Very heavy when we get into calculus later on. They aren't bad. I know they're intimidating. For you guys, where you've seen that E maybe in math classes when you talked about exponential growth and exponential decay. Alright, so why that comes into play here is because when we charge a capacitor and we discharge a capacitor, it charges exponentially and it dissipates exponentially. So that's very, very, very important. Alright, so VC, that's the voltage across the capacitor, so that's the 12 volts, okay? And then we have our final voltage, that's what it gets to when it's fully charged, so in this case it can get to 12 volts. Alright, and V initial, that's any voltage across the capacitor it begins. So maybe that capacitor didn't fully need to discharge because something switched. Alright, it might have started. But in general, when we do these calculations, our initial voltage on the capacitor, we are assuming the circuit isn't on at that particular second, or that it hasn't been charged at all because everything was dissipated once the switch closed. Okay? So, and if you don't grasp all this right now, that's okay. We're going to apply it. You're going to see it multiple times, but make sure that we're writing down the equations, because mostly at this level where we're at, we're just going to be substituting in values, all right, and being able to do some basic calculations. All right, so this is discharging the capacitor. All right, so what happens is, notice the difference in this on the switch closed from A to B. You can, pause the video and backtrack, or I'll just flip back real quick. This was charging, right? Notice and then when we discharge, the switch went from A to B. So now that battery is no longer connected to the capacitor, which means the capacitor is supplying a charge to the circuit momentarily. And I say momentarily because, it's going to be in milliseconds, microseconds. And once again, it's all based on taking that resistor value of 3,000 times 4.7 microfarads. Remember, capacitors are in farads. So it's really just 3,000 times, 4.7 times 10 to the minus 6. That's our time constant. And that's what's going to go under time right there. But make sure you write down this equation. So this is the equation for discharging a capacitor. So VC equals V final minus V initial times E to the minus T over RC. If I accidentally say tau, it's just habit from other classes, but it's e to the minus t over RC here. All right, so the capacitor ideally is going to charge or discharge, sorry, to 0 volts. All right, and it's all going to discharge through that 3 kilo ohm capacitor or resistor. So make sure we understand that we have the equation for capacitor's charging cycle and its discharging cycle. So make sure that those are in your notes. So let's take a look at what's going on here graphically. So we're always going to say the terminology that we're always going to go over. Hey, imagine a switch has been in a position for a long time. All right. I don't like that term, but in every single electrical book we use, the university level, it always refers to that verbiage, and it's confusing because a long time to you or I might be 6 months or a year. A long time to a capacitor is in milliseconds and microseconds. Okay, that's what we're considering a long time. A long time is like a millisecond to a capacitor. So we've just got to get a frame of reference of what a long time really means. All right, so what does this graph represent? This graph represents the capacitor charging and the capacitor discharging. All right, so this is graphically, it's a snippet, it looks like out of an oscilloscope, right, that we use in multi-sim. But what's going on here? So, all right, if we look on the left side of the graph, all right, we're starting out, we're initially at 0 volts on the capacitor. The switch goes to A, and we start charging, okay, instantaneously. Like it's almost instantaneously charged. It's exponential, right? It's the equation. We get up to 12 volts, and then we start to level out, and we're at 12 volts. We've made it through 5 time constants. And then what happens? We flip the switch from A to B, and the capacitor discharges. So that's that exponential decay curve that you see. So that's how fast. All right, and how fast does this thing discharge? All right, we're reading the square on the screen, right? Remember, 1 square is 20 milliseconds. So if we look, it takes about 3 squares for this thing to discharge. All right, so it's going to take a total of about 60 milliseconds to discharge. If we look on the left-hand side of the graph, okay, it takes almost 3 squares for it to, what? Fully charge. So it takes about 60 milliseconds to charge, 60 milliseconds to discharge. Pretty close there. We're just estimating. All right, there's more of a precise calculation. All right, but this is what we're seeing on the inside of the 555 timer. All the component, the flip-flops we're going to cover in here, but all the other components that you see in here, it has component 1, component 2. Those are op amps, okay? Those are amplifiers. And then the straight line with the arrow pointing down where it says T1, transistor 1, okay? That's a BJT transistor, a bipolar junction transistor. It can be NPN, PNP, and those are what we use for electronic switching. All right, we'll get into that in more of the advanced course. Any of you guys that make a Tesla coil, you'll be using one of those as well. Okay, so remember that there's 8 pins on that 555 timer. Each one of those means something. So VCC, so pin 8 is power. Okay, and then pin 1 down below is ground. So those are pin 8 and pin 1. It's very important that we plug things into the right pin on the 555 timer if we have to breadboard, or this is why it was important that we put it in that dice calculator. All right, so we have some different things we got to look at here. We got different resistors, all right? And this is all strictly what's internal. Okay, so you don't get to see any of this. That flip-flop, we're going to use D flip-flops, but this is an SR flip-flop. It's a set reset, all right? And we have Q, which is an output symbol, and then we have the opposite of Q. So kind of a preview of what's to come. If Q is 1, Q bar will be 0. And vice versa, there's a way that we reset the flip-flop. So if Q was 0, Q bar would be 1. And notice that Q bar is going to that transistor, so it's electrical switching. So a 0, tells us to go to ground, or a 1 tells us to calculate an output voltage. So we use that electrical switching inside. But that'll make more sense someday when we cover transistors and go through there. All right, but we have our control voltage, our threshold voltage, and our trigger voltage. Those are what's all going to come in, and that affects the set and reset on that flip-flop. All right, so I want you to think about the flip-flop. If we're setting and resetting, I want you to think of like a square wave signal where we might have set equal to 1 and reset equal to 0. All right, so when we hit like set, it puts it to 1. If we hit reset, it sends the signal to 0. So just kind of some basics. We're going to get into that. All right, and here's what's really going on. So the external resistance that we care about is the RA, the RB, and the C. Okay, and then we have an output out there on the LED that's just going to show our oscillation. So what I want you to think about is on our breadboard companion, the flashing light that's on there. So as we change the variable resistor on our breadboard companion, we can make that LED flash really fast or flash really slow. But what that's really doing is outputting our 5-volt square wave, and it's changing the frequency on our clock. Okay, and that's all gonna make this will all come together. Okay, I don't expect you to memorize everything that's inside the 555 timer, but what we do need to know is how we charge and discharge. All right, and how RA, RB, and C, okay, our RC circuit affects our 555 timer. All right, so what are we essentially doing? We're kind of going like analog to digital here in the most part. Okay, so we have VC. Okay, so let's talk about time high. That's where we want to calculate when we're oscillating high. So the output is high, means we're outputting, for right now, we're outputting like a 1 or a 5 volts. Does that make sense? Or something that's true. Now I want you to start thinking about those sort of things, because when we get into our logic gates here soon, that'll make a big difference. All right, so the output is high. Well, the capacitor is charging through RA plus RB. So you need to write this equation down, time high. Okay, and don't worry about where that 0.693 comes from. Just make sure that you know that you need to use it. You're going to take 0.693 RA plus RB times the capacitor value. Okay, so that's how we calculate time high. So on a test, I'm going to ask you to calculate time high, time low, duty cycle, frequency, period, all right, and those sort of things. We're going to go through the examples here in a second. So remember, time high on the square wave is when it's at 5 volts. So if we notice what's really happening there, that VC, as that capacitor is charging and discharging, okay? So time high as it's oscillating. So think of as it's growing, all right? It's getting to the voltage that we're looking at, so time high. All right, so how do we calculate time low? Okay, this is time low has to do when the capacitor is discharging. So if I'm going to step back a little bit here on this slide. Time high, what are we doing right here? We're getting 5 volts. We're going through RA, we're going through RB, and we're going through the capacitor. Okay, so that's charging the capacitor. Then watch what happens. So that's what's highlighted in blue. This is discharging the capacitor. So what's happening, right? We've flipped a switch now, and we're taking this violet path here. We're going through the transistor now. We're discharging. So now we're using that transistor, all right, and we're gaining an output of 0 instead of an output of 5 or whatever the voltage is that we have on here, okay? So we got time low. Make sure you write this equation down. It's 0.693 RB times C, the capacitor. So just to reiterate, all right, this is the low time is when the capacitor is discharging. The high time is when the capacitor is charging. So that's how we create the oscillation signal, is using the capacitor. Okay, charging, discharging, charging, discharging, charging, discharging, and that's how we create, like, you know, something like a clock signal or an oscillation. All right, and we're able to kind of control how fast that oscillation does. So here's some calculations. So if we want to calculate the period, and we already wrote down, so we're just going to work kind of like left to right, top to bottom sort of thing. All right, so if we look at the period here, the period, we wrote down time high, and we already wrote down time low. And we should know this from signal analysis, that to get the period, the total period is the amount that it's high plus the amount that it's low. So we need one, cycle or one period. So as long as you know how to calculate time high and you know how to calculate time low, you literally just use those equations. All right, we add time high plus time low. All right, and this is just some algebra simplification. So for you, if you know how to do time high and time low, you can calculate each one of those and add them together and you'll get the period. Or if we want just the period equation, okay, remember the period is capital T, you're going to take 0.693 times the quantity. Anytime I say quantity, we're talking about something in parentheses, of resistor A plus 2 times resistor B times the capacitor value. Alright, so we're going to substitute in. I'm going to give you a problem that has RA, RB, and C, and you're going to tell me the period. Remember, the easiest thing to calculate then is the frequency. The frequency is 1 divided by the period. So if you get the period, take 1 divided by it. Just remember, when you do the frequency, that you have to put period back into seconds. Alright, we got to remember that from doing the signal analysis. So if the period was 16 milliseconds, you had to use 0.016 seconds. So make sure when you're doing frequency and you're using the period to calculate frequency that you put period back into seconds. Alright? And then lastly, the duty cycle. Remember, the duty cycle is only based on time high. We learned that last lecture in signal analysis. So you have to take the time high divided by the period. Time high divided by the period times 100%. And there's algebra through all this. I just wanted to show you guys, where everything fits in and how you calculate it. But essentially, if you already know what time high and you already know what the period is, just divide those two numbers and multiply by 100%. Okay? Alright, so let's take a look at an example here. So we have this 555 timer, and we want to calculate the circuit's period, frequency, and duty cycle. Well, we have to pluck off the important pieces here. What are the important pieces? RA, RB, and C, the capacitor value. Okay? Please remember that capacitor is 6.8 microfarads. So make sure that you put it into farads when you do the calculation. So remember, that means we have to move the decimal place 6 places to the left. Or, in parentheses, you're going to have 6.8 times 10 to the minus 6 when you do this calculation. Don't use 6.8 because you'll be wrong. And I promise you, on a quiz or a test, I will put 6.8 as one of your answer choices when you multiply by it. Alright? So let's walk through this problem. Really, it's a matter of just stepping back, having your notes next to you, and taking a look at the equations we have. So the equation for finding the period was what? 0.693 times the quantity of RA plus 2RB times C. So substitute in your values, and please remember, alright, that I want you to use 6.8 times 10 to the minus 6 right there. I want you to make sure that you're in farads and not microfarads. That way there's no confusion when you get your answer. So you should be able to, I want you guys to make sure you pause this, not right this second, but when I'm done, pause it sometime, and I want you to work through, use your calculator, and make sure that you get all of these exact numbers. If you're not getting any of these, or something's not right, or you can't use your calculator correctly, let me know in class and we'll rework through them. Alright, and I'll show you, make sure we're punching everything into the calculator correctly. Alright, so once we have the period, we take 1 divided by period to get the frequency. This is all stuff we did last section and last lecture as well. Same with the duty cycle. Alright, time high divided by the period. I know it's written out as RA plus RB divided by RA plus 2RB, right? That's a simplified version if we just have the resistors. But because why do we want to use it this way? We didn't calculate time high. We only calculated what? The period. So it kind of depends on what you're given. If you're given the resistors, just use the resistors. RA plus RB divided by RA plus 2RB times 100%. So our duty cycle is 76%. So make sure that you have all this stuff written down in your notes. Alright, because then you'd have to take the time to find the time high equation and then use the time high in the period. You could do it that way as well. It's not wrong. Just sometimes, work smarter, not harder, so work with what's given to you. Don't make the problem harder than it needs to be. Alright, so we found the 3 things. We found the period, the frequency, and the duty cycle. So you'd have a question like that on your test. Alright, let's take a look at this now. We've got to kind of go the other direction. We have a 555 timer. We want to calculate what RA and RB are. So we're going to work backwards because we want to make sure that the oscillation is at a specific frequency. We want it at 2.5 kilohertz operating at 60% duty cycle. And if we look at the schematic down here, we're given the capacitor value of 0.47 microfarads. Alright, so make sure you always write down your givens. What are you given? You're given a frequency of 2.5 kilohertz, you're given the duty cycle of 60%, and you have a capacitance of 0.47 microfarads. So you're going to have to use what's given to you and look at your list of equations. What can I substitute in to get RA and RB? So let's take a look at it. Well, using the frequency, we can get the period. Alright, so 1 divided by 2.5 kilohertz. Please remember to use 1 divided by 2,500. Alright, so that we're in hertz, and you're going to get 400 microseconds. That's really going to help us out because, why? 400 microseconds is our period. Now that we know our period, and we know the capacitor, we can substitute this in. This is probably as complicated as it gets. If you remember from math, we're going to end up with 2 equations, 2 unknowns. So we can either set them equal to each other, or we can solve for one variable and then plug it in and get the other variable, or we can use a matrix. There's a couple different ways to do that. Most of you guys haven't done a matrix, so I don't know if we'll hit that one very hard. But use what's given to you. Alright, so you know the period, and you know the capacitance. So we can solve the equation here. So we have T equals 0.693 times RA plus 2RB times C, and we set that equal to 400 microseconds. And then we substitute in the given value of the capacitor. Okay, so we have 0.693 times RA plus 2RB times 0.47 microfarads equals 400 microseconds. So we're going to solve that equation in terms of RA plus 2RB. Those are our unknowns. So we want to get our unknowns on one side of the equation and our knowns on the other. So you got to simplify those numbers down. So RA plus 2RB ends up equaling 1,228 ohms. Okay? Next, we're going to use, so we're going to walk away from that for a second. And we're going to use the duty cycle that was given to us, all right, to calculate RA and RB, to find RA and RB, so we can use it to find one of the variables and set them equal to each other. Okay, so using the duty cycle as RA plus RB divided by RA plus 2RB, we're going to set that equal to 60%, and we know we got to divide by 100%, so we get 0.6. Now, we have to hone us in on our algebra skills here. Since RA plus RB is being divided by RA plus 2RB, we undo division with multiplication. So we're going to multiply both sides of the equation by RA plus 2RB. On the left-hand side, it's going to cancel out and get 1, because it will be the same thing over itself. On the right-hand side, it's going to multiply 0 by 0.6. So now we have RA plus RB equals 0.6 times RA plus 0.6 times 2, which gives us 0.12 RB. So now, okay, we're able to get RA in terms of RB. So we have 2 equations to unknown, so we got to solve for one of those on the right-hand side. So let's solve for RA algebraically. If you need help with the algebra, let me know in class. I just kind of want to be able to get through this. RA is equal to 0.5 RB. So now we have 2 equations, 2 unknowns. So we have to use substitution, I would say, is the best method for you. You know what RA is now. You're going to take RA and substitute it into the equation on the left. So we have 2 equations that we don't know everything to, right? The one on the left, which is RA plus 2RB equaling 1228. And then we have the other equation, RA equals 0.5 times RB. So those are our 2 equations and our 2 unknowns. So we're going to take the one on the right-hand side, okay, and substitute it in for the RA on the left-hand side. So that entire equation will be in terms of RB. Okay, so if we do that, this is just from the previous page here. All right, we have RA equals 0.5 times RB. I'm going to substitute that in on the left. I'm going to replace that RA with 0.5 RB. Okay, so when we replace RA with 0.5 RB, and then we have plus 2 RB equals 1228. We can solve that for RB now, just doing basic algebra. Now we get RB equal to 491.23. Now that we know RB, we can find RA. Alright, I would just take RB and move over to the duty cycle, and if you just take RB times 0.5, you'll get RA. You can substitute RB back into the other equation as well to find RA. So what I've shown here at the bottom piece for this one is if we're got to find RA, and we know RB is 491, RA plus 2 times 491 equals 1228. Subtract the 982, so RA is 245. So there's two ways of finding RA. You can plug it back into either equation. I personally, even though I've shown you the long way here, would plug it into the duty cycle and just take that 0.5 times RB, so half of 491 is 245,618. Alright, that's probably one of the more complicated ones where we got to work backwards and find the resistor values that create a specific oscillation. But sometimes you're looking for that frequency, right? Here's where, right, if anybody that has, you want to sync your remote controls, right, so that you're operating at the right frequency. Well, to you, that's just hitting a button, right? Or like your Bluetooth technology on your phone, or a hotspot, or things like that. But that's all doing the same kind of thing, because when you're using, your phone as a hotspot, it's just really giving off a frequency. A Bluetooth signal is really a frequency. All right, so when you want to sync your Bluetooths up, you're trying to match the specific frequencies. All right, and you use a resistor and capacitor to do that in general. Alright, so if we get into like a little bit more, this is just going further with some things here on the 555 timer. Alright, if we take a look at what's really going on as we do a signal analysis on this sucker. Okay, so what do we want to look at here? We got VC, we got reset, set, we have our output Q bar, we have our T1, okay, and we have our Q. So we have high, lows, on, offs, all those different things. So if we take a look at the initial position here, what's happened? Okay, we got VC that's exponentially growing up. Okay, our reset is at what? Low, which means it's at 0. Our set's dropping to low. Alright, our Q bar is low, which means Q has to be high. Alright, it means our transistor in this case is off. Okay? If we look at each one of those points. Now what happens at the next point here? If we take a look at this, what's happened to the capacitor? VC, remember that's the voltage across the capacitor. The capacitor is fully charged, and then what? Starts to discharge. So as the capacitor is discharging, why did it discharge? Because we hit reset. Notice the capacitor is fully charged and we hit the reset button, which tells the capacitor to do what? Recharge. Alright, so what happens when we hit reset? Our Q bar goes high. Alright, and our T1, okay, transistor 1, turns on. Okay, and our Q drops to low. So next, what happens is that capacitor, we hit set. The capacitor hasn't fully discharged yet. Okay, the capacitor hasn't fully discharged yet, but we hit the set button. So notice there's a spike in set. It went from 0 to 1 just for a second. Alright, but what happens to our set reset on our Q? Look at what's going on there. Q bar was at 1, and then we hit set and it dropped to 0, which means Q was at what? 0, and now it's back to 1. We set Q to 1. That's really what that means when we do set and reset. So when I hit the set button, it made it so Q was outputting a 1, which means Q bar dropped. Look at what happened to the transistor when we hit set. The transistor was at what? 1, and it dropped to 0. Alright, so it completed that path to ground then. So that's how the transistor switches things on and off. Okay, so let's look. Just take a look. We're just looking at these points right here. When we actually hit the set button, what happened to the output and the transistor, and what happens is we are creating an oscillation. Set, reset, set, reset. That's on the, remember, you aren't physically hitting the reset button. I keep saying we hit the reset. But what's happening is it's using itself to recycle itself, if that makes sense. Okay? And we adjust the RA, RB so that we get a specific, like what we just calculated before, so we get a specific oscillation frequency. Okay, the frequency we're looking at is what? Either Q bar or Q. We can choose whichever signal we want to. In this particular case, it's choosing Q. Alright, so we have Q going what? You can look at that it has a long high time and a short low time. So it's going high, low, high, low. That's really, you know, the LED going on, off, on, off, on, off. So the set reset is not you physically hitting a set and reset button and you're oscillating it. The set reset's a flip-flop that's internal to the 555 timer. So, and the transistor is the one that's sitting there changing the values. So that's how we use electronic switching to go back and forth. So that's why transistors were a huge difference maker for us in the electronics world a while back. And that's why you can have the internet and a calculator and a computer in the palm of your hand in your cell phone now. All thanks to that kind of technology. Okay? So, now, if we take a look at this chart here, when the output's high, the capacitor is charging through RA and RB. When the capacitor is discharging, okay, and it's discharging and we're creating that low signal, okay, through RB. I don't expect you to grasp all of this at one time, but we're charging, alright, so what's happening? Q is on, or the LED is on, and when we're discharging, the LED is off. So charging, LED's on, discharging, LED's off. Charging, discharging, charging, discharging, on, off, okay? High, low, and I want you to start thinking about this. True, false, true, false. Okay, we're going to get into that soon on what those really mean. Okay, different design equations. So if we want to just go through here, all right, this is a lot more work than I really want you to use a natural log to solve. All right, but this is kind of how you calculate an oscillator's high time if you need to. Okay, I'm going to make it easy for you so that you don't have to go through all of this. Just use the equations down below. This is just showing how we calculate using that initial equation that I gave you to get to this. Just know the equations right now. We're going to get basic in here. This is a whole other level on my MTSU class that we teach for this. So, time high, all right, use the calculations below on the right. Same with time low, okay. I have it here where I'm explaining how you actually solve this. The math is a little bit beyond you. It's a little bit more towards calculus where we got to take the natural log on both sides. But this is essentially how we would calculate this out. Alright, so just to recap, alright, making sure we have the equations here for period, duty cycle, and frequency. Making sure that you guys, that we're having those. Just remember, for the most part, it's just going to be you guys being able to substitute values into these equations and solve. So both of the examples we did, I would expect you to be able to redo either one of those on a test. The second one, a little bit longer. Alright, and I won't make you memorize the equations for all of those, like time high, time low, duty cycle, charging, discharging, things like that. I won't make you memorize all those, so you will be able to write those down, but they have to be your handwritten notes and equations. You can't, I don't want you to type them up or share any of those with anybody. So it has to be handwritten in your handwriting and your pencil or pen. Okay? Alright, so after this we'll take the lecture quiz, and then we will be in the lab doing our calculations and working through everything on the computer.